I have my backup pen and my regular one. I put them side by side and just plain mess that one up. Okay, so let me share screen. And just for the sake of people who will be coming in late, to add them in, let me get a list here. Okay. Good afternoon, all. I made a co-host so because that way, once I get going on things, hopefully you can let everybody in. And a couple of things I need to do. I want to load up the handout for today. So let me get the chat box up and going. Oh, there it is. All right. I think I just don't know how many to expect of these things, so I'll go ahead and give it another minute or so, and we'll get going a little after one. But here is the handout for the day. And so if one of you is feeling magnanimous and feel like loading up the handout for the day at about like 1:05 or so, just for anybody who strolls in late, that'd be great. And second question, are all of you able to get it from the chat box? Because if you cannot, then I need to email it out. Okay, sorry, I think, oh, I do have the right pen, perfect. Oh, perfect, yeah, so she got it from office hours, so that works out well. Okay, let me, I think I hit admit. Okay, so perfect, so it's all loaded up and ready to go. Once, okay, I think this might be at CrowdWise then. So I'll go ahead and get rolling on this. So again, my goal is to do pre-lectures for the really important stuff. And so in office hours and then a couple emails got people asking for specific things, and I can add them in office hours. But for instance, two people have asked about inertia, and really just want to emphasize this inertia. And I've looked at that guide for 2015 when they released it, when they rewrote it in 2017, and then the one online right now. And nowhere in any three printings from AAMC's guide is inertia listed or is momentum. Now, I have, I think, one or two momentum questions out of the 6,000 or so in the book, just in case they go off the rails. But there's a handful of things that actually weren't covered. Yeah, it's buried in a few. The concept in the question itself, maybe in the passage they might mention it, so I do that. But pendulums, yeah, pendulums are interesting. So they're not listed, but they've definitely been on the test as an energy concept. So you have to know where they have highest potential energy, highest kinetic energy. So you have to be able to read the energy diagram, and you still have to know about frequency. That's popped up. But the details of them, not quite as much as they once were. But yeah, I'm going to go over pendulums because those are still tested. Yeah, I have the pendulum equations on the formula sheet, and the main thing is just because they're pretty much the exact same as the spring equations, except everywhere you see a K in one, you see a G in the other. Everywhere you see an M in one, you see an L in the other. But the big thing is you got to know the energetics, the work and energy, and then you have to know periodic motion in the sense that you have to know what period means, what phases are, what the frequency is, and so a pendulum. And I think the reason springs are more common now in the MCAT is the two devices in our body that have periodic behavior are both springs. Our lung compresses and then relaxes, compresses and relaxes, and our lung, which expands and relaxes, expands and relaxes. So I'm definitely have to be able to compare that. Pendulums, they did have a weird passage years ago where they lifted, like a doctor had somebody's leg lifted off the ground, and they'd support it just behind the knee, and they lift their leg up and they wanted to see like what its period was when it swung back and forth, just releasing it. And so it was just kind of a weird passage where they wanted to decide whether what would happen if the knee was arthritic to the period. And the key thing you had to recognize is the period shouldn't change. What would change is the amplitude. It would, because of the additional friction, it wouldn't swing as smoothly. But outside of that, yeah, I thought I thought there were 12 as well too, but everything I sent out said 1. So are we on the same page with this? It is 1 o'clock, right? Somehow 12, and I got to admit, I was wondering the same thing. I actually was looking around. So it is 1. But yeah, so 12 is the Wednesday office hours. There's so many different things I do. So Sundays at 5 for office hours, Mondays are at 4, Wednesdays are at 12 for office hours, and then Fridays are 1 for this. Yeah, and yeah, I know it's, but welcome to the wonderful world of this field. You can say it, but it just, for whatever reason, there's too many pieces of information coming in, and it always gets messed up. Yeah, yeah. Google Calendar or any of those programs are so awesome, but apparently we don't use one. So moving on, acid base, very very major topic. I can, but let me do a catch-all when there's a few more things to put into it. So pendulums would be a small part of it. That's going to be maybe 20 minutes at the most for what we need. So I'm going to catch a few other things. So as people suggest other things, I'll do a catch-all. And so pendulums will be on it. I won't do inertia because the thought of teaching something that isn't tested, even though it may help, even though understanding it certainly helps with other things like energetics, it's just, I don't know, it seemed sort of silly that it was that, like, moment of inertia, angular momentum, and angular velocity are not tested on the MCAT. However, mv squared over r is. So, well, thank you. But anyway, let's go ahead and get rolling on this. So acid base, the key thing that most people do on acid bases, and I'm assuming this is true for most of you, how many learned acids really well and completely fake your way through bases? An honest answer, how many just do pH? You don't even stop to think about pOH other than 14 minus. You know your strong acids, you know titration curves where you have an acid, you add a little base to it. It's what we do. Has it worked so far? Has it worked to know one and be able to work your way through the other? Yep, it works beautifully. I hope you do that on a lot of your studying, because there's 2 things that happen. Number one, you actually build confidence. When you have enough confidence in yourself to say, look, I know this one so well, I can figure this other one out. That's when you start doing really well in the MCAT. Number 2, cuts down the workload. And that's how we're going to treat it. We're going to treat it as acids. And oh yeah, by the way, there's some bases. So have to know your fundamental definitions. And you may not have to know them like precisely to get a question right, but they definitely have answer choices that will include like Bronsted-Lowry acid. And knowing Bronsted-Lowry may not be important at all. Just knowing what an acid is will be important. But the more you know, the better you're going to be. So I want to start with just those definitions. We typically think of an acid as something that generates H+, and we typically think of a base as something that generates OH-. This is just kind of our standard perspective. So beyond any definition, just an acid is going to spit out some H+, a base is going to spit out some OH-. This is kind of the Arrhenius definition and kind of the Bronsted-Lowry. It's a hybrid of both. I'm choosing my colors carefully today, and I want to say why. So is there any reason why I would be doing the color scheme that I'm doing? Just Off the top of your head, any reason why you think that might be a reasonable color scheme to do? It is a mnemonic for what though? So why would I know acid red, base blue? Does that ever pop up in any aspect of acid-base chemistry? Litmus paper. Absolutely right. Perfect. So where it can pop up is there's no way they're going to give you a question. pH 4.7 when turn litmus paper red, yellow, blue, or green. They don't do that. But what they do is they may say that, let's say you do some chemical experiment and the product, when you isolate it, turns litmus paper red. Does that piece of information help you at all in that chemical reaction? So for instance, I do some reaction and I generate a compound that turns litmus paper red. Then let me give you the reaction. You tell me what kind of reaction just happened. So I treated whatever it was, some unknown, with CO3, and I got compound X, and compound X turns litmus paper red. So can you tell me what you think might have happened in that reaction? And you have enough information, you just have to be very confident in your information. So mainly, what kind of compound is compound X? Would you agree it's acidic? And how many would agree turning litmus paper red is acidic? Okay, so that's going to be our starting point. So I know whatever this compound is an acid. So the compounds that are acidic in OChem are carboxylic acids, thiols, phenols, protonated amines, so the conjugate acid of ammonia, and amines. Those are your acidic compounds. Realistically, we can probably eliminate thiol and amine right away just because they're not as common. But what I want you to tell me then, between that information, turn litmus red, so therefore I've narrowed down to 4 possibilities, and that compound right there, what can you give me a good educated guess at what went on in this reaction? Chances are X is what compound? Is it a carboxylic acid, a thiol, a phenol, or a protonated amine? So we got 1 vote for carboxylic acid. Perfect. Got 2 votes from the same person. So far the total count's 1-0 for carboxylic acid versus everything else. No need for recount. It's perfect. That's exactly what it is. So does it ever happen? Does a primary alcohol or an aldehyde, can both of those go on to form a carboxylic acid when we use an oxidizing agent like chromate? Is that a reasonable OChem reaction? Is that one you've ever seen before? KMNO4 in base or CO3 in acid would generate a carboxylic acid. They're oxidizing agents. Okay, so the big thing on this then is knowing litmus paper turns red with acid is not something that's going to directly get you a question right. It's indirectly going to give you one extra piece of information to be able to make these sorts of decisions. And so it isn't that knowing a fact helps you, it's knowing a fact in context with other facts to make decisions. That's what we're going to have to do. So red with acid, blue with base for litmus paper. Okay. Is it okay to erase this at this point? Well, I'm going to erase it. I guess I should give you a heads up. I need the space for everything else coming in. But 3, 2, 1, on. And again, always want to justify why we're memorizing things in the context of the test. So how you apply it. So hopefully litmus paper red would have been a good, useful tip on that question. Okay, the definitions. How many have heard proton donor and proton acceptor? Does that sound reasonable? One donates an H+, one accepts an H+. Whose definition is that? Just a random fact, but The university I went to, Dr. Seuss was one of our major donors. In fact, our library is named after said Dr. Seuss. Hence, in his honor, everything we ever learned was always in Dr. Seuss-like poetry. So Bronsted-Lowry acid was a Bro-Low-Pro-Do. Bro-Low-Pro-Do. I sound like an idiot? Do I care? Not in the least. Bro-Low-Pro-Do tells me Bronsted-Lowry proton donor. So, do I sound like an idiot? Yes. Do I care? Nope. So perfect. Okay, so that's a proton donor. And again, if one is a proton donor, the other one then is proton acceptor. Okay, I'm going to get rid of my mnemonic and just put up that. So Bronsted-Lowry. Key thing, all these definitions that you're going to have piled onto you, there's so many of them. And the reason there's so many is because different solvents can be involved. So initially, we just thought about water as a solvent, but then somewhere along the line, Bronsted-Lowry said, well, what about ethanol? Or what about amines or other solvents we could use? As long as they can transfer a proton, an H+, then this definition will work. Okay, we also have Lewis definition. Lewis definition is more friendly in terms of OChem. So for instance, hydrochloric acid we consider a strong acid in water, but if you put hydrochloric acid into benzene, would it dissociate into H+ and Cl- in a solvent like benzene, an aprotic nonpolar? Not going to dissolve. Not going to, I mean, it might dissolve lightly, but it's certainly not going to dissociate into H+ and Cl-. So when we use organic solvents, we have to use things that act just like H+. So if I considered this reaction, if I can have that attack an H+, and then a nucleophile come in, I can certainly make the electrophile more reactive. But what if I did it this way? Is BF3 doing the exact same thing H+ is doing in this picture as H+ is in the other one? Yeah, it's just accepting electrons. The difference is BF3 is polar or non-polar. Perfect, non-polar. So will it dissolve into benzene? Will BF3 go into benzene easily? Sure. So what we're trying to do is get something that accepts an electron pair like H+ does, but it's non-polar. So this would be your Bronsted-Lowry, your Arrhenius acid. This is your Lewis acid. Okay, so I want to toss the mnemonic up there. I think we did it once before. It worked well. What am I missing in my word Lewis base? How many E's total? 2, because to be a Lewis base, you need 2 E's. So it's electron pair donor. So Lewis base has 2 E's, it's electron pair donor. So Lewis acid is missing. Yeah, dumb little things like this make all the difference in the world, because you just remember that there's 2 E's in a Lewis base, so there's 2 E's on a Lewis base. Okay, so far so good. I'm going to erase this as well. So if you were screenshotting, 3, 2, 1, and gone. So electron acceptor, keep in mind, it is electron pair and electron pair. Perfect. Again, any solvent. So I mentioned BF3, AlCl3, another electron poor central atom that's neutral. Electron pair donors, these are also really good nucleophiles. So I'm going to just make a little note. They're also nucleophiles, which I ran out of room, so I'm just saying nucleo. And then the last definition, this is the one we're going to push in GChem. But again, just like electrochemistry, is acid base strictly a GChem topic, or is it GChem, OChem, biochem, and physio? It's all of them. You have to know how it applies every which place. So nothing like giving a passage on acidosis and then asking for the pH of a solution. So GChem question in the middle of a physiology topic. By the way, what is acidosis? Excessive acid. Perfect. When your blood is too acidic, or I guess technically your body in general is too acidic, but perfect. So how would one get acidosis in your blood? I don't get how could that happen? Seems like a strange thing. So hyperventilating would offload or retain CO2. Yeah, so CO2 accumulation. CO2 is acidic. So how many learned CO2 added to water turns into H2CO3? So carbonic acid. So hyperventilating actually offloads CO2 at a faster rate. So you actually get too little acid, you become alkalotic. But if you have a disorder such as, let's say, crispy lung disorder, emphysema, where alveoli lose their elasticity, then what would happen? It would have been taught in physiology, so, and possibly biochem as well. Yeah, and I'm assuming it's a physio subject. A really good GChem teacher may allude to it, but yeah, so if you consider condition, let's say emphysema, what happens to a patient who has chronic emphysema or long-term emphysema? Two GChem predictable things. Perfect, hard to remove CO2. They have less alveoli or effective crossing points. So two things are going to happen to that patient. First thing, if they can get less CO2 across, does their blood start to accumulate and build up CO2? Perfect. They're going to become acidotic. The second thing is their body has to compensate because you got to offload your acid somehow. So what would you predict for their urine pH? Higher or lower than a normal person? Somebody who's got respiratory acidosis? Lower pH, because if they can't get rid of the acid by exhaling, can't get rid of it by respiratory means, and they get rid of it by metabolic means. They offload their H+. So the urine pH should be a little lower. Number two, they get a condition known as barrel chesting. And so how many have ever heard this, or how many at the very least can look it up on the internet and look at what barrel chesting physically looks like? Their thoracic cavity, the intercostal muscles literally weaken, and their rib cage, the thoracic cavity literally expands so that they look like this barrel-chested human being. It's massive. And that allows their lungs, their pleural sac, to expand more or less if their chest cavity is bigger. Allows it to expand more. So their lung can expand to a greater volume. If volume goes up, what happens to pressure? When the PV equals 100T, if volume goes up, pressure goes down. Are they literally expanding their lungs more to create a vacuum to literally suck CO2 across the alveoli? So even though they have less points of transfer, less alveoli, do they get more CO2 going across each alveoli by creating a larger pressure gradient, a bigger pressure difference? Okay, so did we just use PV equals 100T and acid-base chemistry to explain a physiology disorder such as emphysema? Big picture, how do you apply it? And number two, how many of us find it so much cooler when you can apply it? PV equals nRT makes a lot more sense when thinking about barrel chesting than it does when hot air balloon goes up in the air and this happens. Yep, the more you can apply it to real life, and especially real life things you like, the better. Okay, so not sure how I got off on that tangent, but absolutely critical that you know how this stuff ties into all the other material. So acidosis, definitely fair game for the MCAT, and kind of a cool way to introduce acid-base GChem to you while giving you a physio example. Okay, somebody mentioned blood. Is blood oil-based or water-based? I can't remember. Yeah, in acidosis, your blood pH will be lower. Now, let me ask you something, Alan, when you say this, what exactly is blood pH? And yes, blood is water-based, so that's important. So Arrhenius definitions hold. So what is blood pH? And the beautiful thing, no matter what number you type in there, I'm going to say wrong, partly because I'm just kind of a mean person. But if you told me 7.4, wrong. Okay, so a range, that's perfect. But why would I still yell wrong? Because it's a weird question, because is blood pH consistent? Perfect. Does it change? Is arterial pH different than venous pH? And is that absolutely critical to physiology, knowing whether it's red blood or blue blood? Oh, yeah. So blood coming out from the lung to the tissue, arterial blood going out, is oxygenated or deoxygenated? Oxygenated. That means it's rich in O2, poor in CO2, so the pH is going to be high or low. A little bit higher. So 7.4H. As people were saying 7.35 to 7.45, in that window, definitely. I'm not going to say 7.4-ish. But what about venous blood? So what happens in venous blood? Why would it change? Why is it lower, Jonathan? Okay, so it's got less O2. The O2 has been released, but also higher CO2. CO2 has been released as waste from the tissue. And so the technical word they use is deoxygenated, but I'm going to use carbonated because I like that word better. Is venous blood carbonated? Is it rich in CO2? CO2 dissolves in, forms carbonic acid, makes pH a little bit lower. So how many have learned it's around 7.2? And in fact, how many have seen the O2 binding curve, which shows at 7.2, O2 doesn't bind, at 7.4, it does bind? Is that something you definitely have dealt with in biochem, O2 binding curve and the dependence on pH? Okay, we're going to hit on that in a bio example in a second. So let me finish off the GChem. But this is the spot we need to go. We need to be able to apply all our acid base from GChem to physio. So acidosis, lung, lung and gas exchange phenomenon. All this is going to tie in. Okay, so Arrhenius yields. Ooh, didn't mean to do that. Sorry. Yields hydronium in water. Base yields hydroxide in water. Perfect. From that, we have pHs to worry about. How many just learned pH less than 7 is acidic and you faked your way through everything else? Higher than 7 is basic. Okay, pretty much a standard thing. I think this is really common. This one you can deduce pretty easily. This is totally true, but we never think about it this way. How many answer choices on each question on the MCAT? Uh-oh. I figured that'd be a straightforward question somebody would answer. So perfect. 4 answer choices on every single question. Perfect. Which means I, as a test writer, if I'm writing a test, do I have to come up with 3 wrong answers every time? Meaning I have to mess with you. So if I can say the same thing 1, 2, 3, 4 different ways, is that going to open up the doors to write some really weird wrong answers? And so part of the reason you want to know as many definitions or different ways to look at things as possible is because the answer choices, and on many occasions, are saying the same thing, but worded in a way you're just not familiar with. And so that's going to be kind of paramount to how we do. Okay, a few other things to toss at you. This equation, am I safe in assuming you have this one memorized so well that you couldn't forget it if you tried? pH is negative log of H plus. I mean, how many have tried to forget it, dissolve it in ethanol or some other means, and you still can't get rid of it? It's always in there. A cerebral tattoo, if you will. Yeah, just one of those things. I'm hoping everybody remembers it. And I did probably one of the worst things you can ever do as a teacher. I said, everybody knows it and everybody gets it. So if you're the one person who's forgotten it, I'm so sorry. That was like terrible. But the reality is it's a common expected known thing. But can I rewrite it to mess with you? Can I write it in a way that nobody knows? And being inherently evil and mean, this is what I want to do. So just want to do some math again. If I take 10 to a power, how does 10 to a power relate? Or 10 to a log, I should say. That was a terrible question I asked. But how many learn 10 to some number and 10 to a log, 10 and log will cancel? And can I put the negative over here by multiplying each side by -1. And so 10 to the log of a power, don't fight the power, just bring the power down. So how many have learned this form of the equation as well? pH is 10 to the minus pH. And that pH is an exponent. Wow, as I'm looking at this, how many see that as exponent-like, but it doesn't look exponent enough? I'm utterly sorry, because this is an exponent, but I guess because it's a lowercase letter, it just didn't look right. But yeah, so that's 10 to the minus pH. Yep, log base 10. Exactly. And although we have log of E, like E based, I think the only spot in Nernst equation that, and I guess the conversion is the only spot that really shows up. So I'm gonna just ignore the thermal aspect and just say we're worried about just straight logs, log base 10. And then how many learned it's 25 degrees Celsius, pH and POH add up to 14? So can I say that this is familiar and this is familiar and this is damn? You better remember that. And so I'm gonna erase and just redo this. I'm so bothered by this that I just want to make sure this is visually clear. A little bit better, hopefully, but okay. Want to throw a question at you? This is going to be an incredibly challenging question. You're going to be overwhelmed and sad and hurt and anguish and go through all 5 coping means before hopefully it'll all fall into place. So be ready for just this emotional experience. In 3, 2, 1, and I totally lied. Sorry. I forgot I changed the slides. I'm so sorry. That'll be down the road. Okay. This equation, does this equation look at all familiar? And again, I'm trying to do physio, biochem. Oh, there's anguish in this too. Thank goodness. Thank you. Oh, total emotional manipulation. Like those people, those jugglers who start to juggle their chainsaw then stop. This is a Henderson-Hasselbalch, exactly. I gotta admit, I have this weird sort of attitude where I didn't think it should take 2 people to do simple algebra. So I just call it the buffer equation. I don't know why we named it after 2 people who had to cheat off each other to do algebra. So what I like about biochem, enzymes are named, reactions are named, things are named for what they do. So even though this is called Henderson-Hasselbalch, you need to recognize that because that's what convention is to call it. I'm going to call it the buffer equation because when do you use this equation? For buffers. Exactly. So does a buffer have an acid, a base, or both? Has to have both. So therefore, you end up having an equation with both. If it's just an acid, the equation should only have an acid. If it's just a base, equation only have a base. But if it's a buffer, it has both a conjugate acid, conjugate base, protonated, deprotonated forms. I use this. So I want to make a big deal both mathematically and intuitively. So intuitively, if the pH is lower than the pKa, and I want to make an analogy, pH is the environment, just like temperature, pH, humidity, things that describe the world around you. Then there's pKa. pKa is like a melting point, a boiling point, aridity constant, how warm you are or how dry you are. So it measures the conditions. So let me give you something, you tell me. If the temperature is lower than the boiling point, what's true? What do you know about that scenario? So temperature is lower than the boiling point, I'm going to tell you it's a gas. Telling the truth or lying as usual. It's a liquid, perfect, because it hasn't evaporated yet. If the temperature is higher than the melting point, it's a solid. True? Or have I lied again? Todd's gonna lie. TGL. False. It's a liquid. And so I really should say if it's less than boiling point, liquid or solid. And this one is liquid or gas. but it can't be that, so it's got to be a liquid. So if temperature is higher than the boil or melting point, lower than boiling point, it's going to be a liquid. So if I know the temperature, that's great. If I know just boiling point, that's great. But do I need to know both to decide what phase it's in? So in other words, so I need to know the environmental condition and the physical property both to make a decision. So conceptually, same story. I'm going to get rid of what I have here, and we're going to apply that same notion to the following. pH describes the environment, pK describes the compound. Is the environment more acidic or less acidic than the compound, at least according to this relationship? The pH is lower, it's more acidic. So you put the compound in an environment that feels acidic. What happens when you feel acidic? You end up protonated or deprotonated? Perfect, protonated. Exactly. So conceptually speaking, I know the protonated form is going to be higher than the deprotonated form. It's going to be mostly in that form. So again, convention, or I guess just perspective, pH is low, it's acidic, gets protonated. From a math perspective, let's do the math here. If the pH is a low number, and this is a high number, then you agree this must be a negative number. Does that seem okay? It can only be true a low number would equal high number plus a negative number. And if you remember logs, if the log of a number is negative, that must mean the numerator is small and the denominator is big. So if the log is negative, that can only be true if protonated is higher concentration. Denominator is bigger than numerator. Protonated is bigger than deprotonated. So log term is negative. Can only be negative if this is true. So how many are okay with that? How many agree that our conceptual perspective matches the math? Okay. So once again, you have a couple choices. Your choice, use math to prove it, or use intuition to deduce it. Which one's better is completely up to you, but there are two routes to it. How many like doing things intuitively, but double checking with math? How many kind of do that just instinctively? Your gut feeling gets it first, and you correct it or double check it. Probably a good habit to get into. Okay, so let's go in a different direction. In this case, pH is higher. If pH is higher, does the solution feel basic or acidic? Solution feels basic now, because when the pH is higher than pK, it's going to be basic. So if this is 3 and that's 2, it still feels basic. If this is 13 and that's 12, still higher, feels basic. So bigger number feels basic. Under base conditions, you deprotonate. So when the pH is higher, it's going to be deprotonated. Same math reasoning as before. If the pH is higher than pKa, so now this is my small number, and this is my big number. This must be a positive number, that log value. And again, if it's negative when numerator is small and denominator is big, then it's positive when numerator is big and denominator is small. Whew, that was a lot of work. Big number over small number gives you, log of that gives you a positive number. So deprotonated has to be greater than protonated. And then same thing, same argument here. Okay, I feel pretty good. Do you agree the only two scenarios, the pH is either going to be less than or higher than pK, or under some instances can actually be equal? Does that ever happen? Can you ever have pH equal to pK? Sure. When pH is equal to pK, what's going to happen? It's going to be mostly protonated, mostly deprotonated, or a perfect balance. Perfect balance. Perfect. Protonated equals deprotonated. If they're equal, this is 1, log of 1 equals 0. Important to remember that mathematically. And then intuitively, if pH equals pK, it must be a balance of the two. Okay, so I want you to help me out with something. I'm going to look at the way something exists at pH 1, highly acidic, 4, mildly acidic, 7, neutral, 10, mildly basic, and 13, strongly basic. So if I put NH3 or NH4 plus in those conditions, it's protonated here, protonated here, protonated here, deprotonated here, deprotonated here. From this list, can you tell me what the pK is for NH4 plus? So from this table, can you tell me what the pK is? Maybe not exact, but you can give me a range that it fits into. So I'm going to tell you the pK is 6. Do you believe me? TGL. Can't be 6, because if we're 6, then at 7, it would be deprotonated pH higher. From this, I'm going to conclude the pK must be somewhere around here. So what is the pK for amines, or the amino terminal? Pretty good idea to know that roughly. Around 9-ish. Perfect. So depending on the amine, it might be a little higher, a little lower, but around 9-ish. I like it. So I'm going to put that here around 9. That's an approximation sign. Ooh, now I have 2 protons. Can you give me what pK1 and pK2 are based on this list? So between 4 and 7, perfect. Ends up pK1 is 6.4. And then what's the second one? Perfect. Somewhere between 10 and 13. Perfect. Ends up it's around 10.8. Okay. So these are compounds you know. Hopefully you can do it if you don't know one. So off the top of my head, I don't really know the 3 pKs of phosphoric acid, but you can give me an educated guess. So if I told you pK1 for phosphoric acid was 4.4, yes or no? Nope. If I told you it was 1.8, that seems reasonable. PK2, around 7.2. PK3, around 12.8. And then finally, what amino acid is that last one? I think it's phenylalanine. Maybe leucine, serine, can't remember. Got to recognize your amino acids in any sort of way they write them. So this one, so you have 10 seconds, got one answer, 5 or 9, 8, 7, 6, 5, 4, 3, 2, 1. 2 answers. Not sure if shyness is kicked in, but yeah, it's glycine. For the 2 of you answered it. It looks a little weird, but do you recognize amino terminal, carboxyl terminal? 1H is the normal hydrogen on there. Second one must be the second H, so glycine. Glycine's pKs are 2 to 3 and 9 to 10. So is that correct for, does that sound right? 2 to 3 and 9 to 10? Hope so. Those are ones you definitely have to commit to memory. So don't know precise pKs, but know approximate pKs. That said, this is one of the few precise ones you can have to know. Why am I telling you that one is one of the few that you absolutely have to know? Guaranteed you will have to know that on your test, for sure. Because what makes carbonic acid? Blood buffering, pH of the blood, exactly. You have to understand that pK being 6.4 is lower than 7.4, so when you add in carbonic acid to blood, it's going to lower the pH slightly. It's going to lower arterial blood to become venous blood. Okay, as promised before, I'm going to click. So if you're screenshotting, 3, 2, 1, and the aforementioned really challenging question. Yeah, I'll after the question, I'll go back and recap. Yeah, every now and then a question does sound like this. Okay, is that going to happen? From time to time, is a question going to make just about that much sense to you? Okay, so I'm really curious, how do you deal with situations like this? Because quite honestly, you're going to have to do this 5 to 10 times on your MCAT. Make the best of a bad situation where you don't understand what the hell the question's asking. So if you don't understand the question, can you at least try to look at answer choices, make some sense? Look for patterns in the answers. Exactly. Perfect. Find the one that sticks out. Okay. So let's see. Look for the ones that are the same. Look for the ones that are different. Exactly. Everything you're saying is exactly what I hope all of you do instinctively. So what does a POH of 6.11 tell me? Basic. How do you know? Absolutely right. So inverse of pH. So perfect. How many converted to pH of 7 point something, 7.89, said greater than 7, so therefore perfect. So low POH or high pH, basic, perfect. So question may not make sense. That's going to be true. So look at the answer choices, just like you said. Everything you said, I'm lagging behind you. You nailed it. And then, Mo, the question is, you totally knew what you were saying, right? No matter what you typed there, you knew what you were talking about. The beauty of this is, don't lose sleep over little typos. They're just not worth it. They truly are not worth it, because obviously you know exactly what you're doing. And this is a message to everybody. How many of you make those careless sort of typos? Just your mind's going faster than your pencil or your fingertips or whatever going to happen? Don't worry. Those will not cost you. So I thought somebody for sure would be typing it wrong, like spelling everything wrong when you said it. Because 3 of you typed all the time, 2 privately and 1 publicly. And I was hoping somebody would like all time there or something. I don't know. Wishful that you guys are smart asses, but oh well. Moving on. What does this one tell me? This one's a little bit weird, but if I put it in a sentence form, is this saying that hydroxide is about 100 times more prevalent, more concentrated than hydronium? 2 pH gradients, because log of 100 is 2. Perfect. Exactly. So all the things you're saying are totally perfect. And your conclusion then is what? That solution is acidic or basic in choice B. Basic. Okay, so A is basic. B is also basic. Okay, so I'm feeling pretty good, except for my iPad is ahead of my screen. Let me click and have that happen. Perfect. Okay. Rich in electron pair donors. Straight definition. I just don't know whose definition that is. It is basic. Lewis base. Perfect. So that's just straight out knowing the definition of a Lewis base. Turns litmus paper red. Acidic. Just again, straight out memorization. What is your best play on this one then? Probably D. I don't feel completely confident, but I'm good enough. Sesame Street, Big Bird, the greatest MCAT test taker ever, would say one of these things is not like the other, one like is not like the rest, therefore pick it on the MCAT test. I think that's what the exact lyrics are if you listen to Sesame Street. So the one that's the outlier. All of you kind of did this instinctively. The ones who like took the time to type in their strategy, this is what all of you were doing. And I'm hopeful that that's, I don't know, just an approach you can get behind. Oh no, my screens are off times right now. So screenshot if you will, because I have a strange feeling it is going to go away in a second. Oh, there we go. Actually, it's catching up. Okay. Biological applications. 2 I want to talk about, one really fast, one painfully slow. The fast one. This is where that pH is higher than pK or lower than pK is going to come into play. So this compound here is aspirin. How many have taken aspirin at some point in life? This is a drug that you have partaken in at some given point. Okay, so for those who have, I think we all have, how many did it? Because it's an analgesic, it suppresses prostaglandins. Prostaglandins recognize local pain. So analgesic gets rid of pain, but it's also anticoagulant, antipyretic. It works against inflammation. It basically suppresses not just one prostaglandin, but all prostaglandins. So it binds the enzyme responsible for prostaglandin formation, or one of the enzymes in that pathway. And in doing so, does all these wonderful things that we think are good. Okay, how many of you snort it? How many shoot it up? How many suppository? How many take it orally? In general, how do you take aspirin? Is there an entry portal of choice for most of you? Okay, perfect. Which means, do I have to consider the pathway that drug is taking into my body based on the path, the injection point? So an inhaler goes in the lung, don't have to worry about a pH issue. Injection goes into where your target is, don't have to worry about its pathway getting through the body, or not as much. But when you take it orally, does it have to go in the stomach? Is that the first pit stop? Well, from mouth, but eventually, perfect, it's going to go through the esophagus, eventually get in the stomach. The stomach, I think, is really basic, isn't it? Can't remember. You need to teach me some physio? pH about 1.5 to 2-ish, 2.5, so highly acidic. So if the pH is 2, and we mentioned carboxylic acids have pKs around 5, phenols have pKs around 10. So two things are going to happen once it goes in the stomach. Stomach is made up of acid and water. What happens to an ester under acidic conditions? The magic water line. You're going to go hydrolysis. Acidic aqueous conditions will hydrolyze things. So I will have an H and an OH. So keep in mind the carbon gets the OH, the leaving group gets the H. That's how this thing plays out. Okay. So you're going to hydrolyze it. If the pH is 2-ish for the stomach, is that higher or lower than 5 and 10? pH is lower. So gastric situations. I think Lexi got booted somehow. I don't know if I did this. So thank you, Jonathan. Appreciate that. Okay. So that compound then overall is neutral, or that compound is charged? Yeah, so the pH of gastric fluids is 2. 2 is less than 5, so it's going to be protonated. And then 2 is less than 10, so it's going to be protonated. So this site right here is protonated, this site's protonated. And as a consequence, this overall compound is neutral or charged. Neutral, perfect. Further, because these are ortho, right next to each other, this can hydrogen bond here. So this lone pair on this oxygen can actually hydrogen bond with that H, meaning if it can hydrogen bond with itself, do you predict it's going to interact with water more or less because of that ability to form that? Interact less. It ends up, the water solubility of this form of aspirin, the active form of salicylic acid, acetylsalicylic acid, is this one, the salicylic acid. So the active form of aspirin, relatively water insoluble. You have a benzene ring and you have H bonding here, so it doesn't need the water around it as much. So would this have a tendency to stay in the aqueous solution, or would it actually try to slip into the cell membrane? Which is kind of a funky, weird thing. One of the very few compounds, because it's aprotic nonpolar, and it's slightly polar, but I'm going to say, because of H bonding here, it's much less polar than we imagine. Inside the cell membrane, it's planar, and it can actually cross the cell membrane. It's one of very few molecules that can naturally migrate across a cell membrane. So the problem is, when it migrates across the cell membrane, ends up inside the cell, it's no longer in the gastric fluids of the stomach, is it now within the core of the cell? And how many learn cellular pH is around 7.4? Does that number sound somewhat familiar? That the cell is roughly 7.4? Okay, perfect. So 7.4, which means at 7.4, I now have to reconsider these things. 7.4 is less than 10, so this will stay protonated, but is 7.4 higher or lower than 5? Seven point four is now higher than 5. And so because 7.4 is higher, ends up deprotonated. So once it crosses into the cell membrane, does it stay neutral or does it now become an anion? It becomes an anion, exactly, which means can it migrate back across? So is this a back and forth trip or is it just one way? Just one way, which means you start to build up ions within your cell. When you take aspirin, this molecule can migrate in and start forming ions. So even if you decompose this, even if you start breaking it down, you still have a negative charge. So this molecule can't migrate out. There's no channel for it. Channels are way too small. They usually transfer single ions. There's no transporter. So you start building up ions inside the cell. If the body or whatever the organism is, whatever it is, cannot move ions out, the next best thing, can it start bringing water in to dilute it? Can it start undergoing osmosis? And can water start going in to try to dilute the inside of the cell to match outside the cell? Our constant quest for homeostasis. So because the ion concentration is too high inside, water will migrate in. But how many agree, no matter how much water you bring in, no matter what, it cannot be neutral. It's always going to be charged. You're always going to have some ion concentration on the inside greater than neutral on the outside. Which means if you take on too much water, what happens to that cell? You keep pumping water in and pumping water and pumping water in, trying to dilute that. First, it lyses, boom. All those words are correct. So how many have ever heard that when you take too much aspirin, it starts eating away your stomach lining? It causes ulcers, it ruptures your stomach lining, your parietal cells. Perfect. This is exactly how it happens. This molecule becomes neutral and hydrophobic because it hydrogens with itself, crosses into the cell membrane through the cell, like literally through the lipid bilayer, goes in, becomes an ion, sucks water in, you end up destroying your cells. So it's one of those things, as a doctor, you have to decide, is destroying stomach lining worth the positive impact? And depending on the condition, the answer is going to be yes and or no. So this passage then, they give you all this information about how aspirin eats away stomach lining and gives you the diffusion aspect, one-way diffusion, and tells you about all these things, and then osmosis. Is this a GChem, physio, OChem, biochem? What kind of passage did I just describe to you? All of them, exactly. Meaning, is this a perfect thing to throw on the MCAT? Because you can ask them a straight GChem acid-base question. You can ask them an OChem structure question. You can ask a cell bio question, ask them about the cell membrane. These are the kind of things that I hope get you a little nervous and a little excited at the same time. How cool is it to combine everything and apply what you know in one subject to help in another? That is the biggest goal of studying for this test. Get your bio knowledge, get your bio perspective, the topic you love the most, to start answering your GChem questions, your OChem questions, and your physics questions when reasonable, when possible. And then realize physics, GChem, and OChem all tie into bio. Everything ties into each other. Okay, second bio topic. Another bio application. We mentioned it a little bit earlier, so I'm going to pound through this a little more quickly. I think this is more of a CP thing myself because it's got chem and physics in it. So bio things that cross over into that area end up CP. And for people who've taken the MCAT, how many would say there is actually a surprisingly large amount of bio/biochem on the chem physics section? I mean, there's things that you learn in bio classes that end up there. And so it might end up having a few chem questions tacked on to what was something you learned in bio. That is a completely reasonable CP passage. And sometimes those are the greatest around for a lot of people. Okay, the heart pumps, arteries push blood out. One to reiterate, oxygenated blood, hence we showed in red, pH 7.4. The color scheme has nothing to do with pH now, has to do with physiology. Gets to the tissue, your 2,3-BPG comes into effect, your deforming hemoglobin comes into effect, whatever the cause and effect of this pathway is, according to the O2 binding curve, when CO2 gets released in the bloodstream, pH goes down, and it prevents O2 from staying bound. It denatures it. I'm going to talk about the denaturing in a second, but how many are okay with this? We've already mentioned this before. Now it's in writing. Carbonated blood, 7.2, oxygenated blood, 7.4. And honestly, how many are bothered by me using the word carbonated blood? It's so unfamiliar because we normally say deoxygenated, but I'm going to say that, yeah, blood soda, fizzy soda. Yep. So nothing more than Coca-Cola is now taking over everything, including your blood. Oh, good question. If you don't mind, I'm gonna toss this question out to everybody and ask for people to take the MCAT. But question proposed was, I had a question about physiology. Should we memorize specific heart valves? It says heart valves or heart values. I'm sorry. Oh, values. Oh, I'm so sorry. I totally misread that. I was going to tell you, yeah, know the 4 valves, but different values in the blood thing. I don't think I'm going to go back and say anything that precise, that nitpicky. They're going to give you a lot of that in the passage, but you should be familiar enough with it that you see what's reasonable and unreasonable. So knowing what the blood pressure is. So for instance, you should know systolic and diastolic. Those are pretty normal. So if I told you somebody's blood pressure was 307 over 210, systolic and diastolic, would you say, yep, totally believe you? Not at all. Okay. If I told you it was around 110 over 70, Todd's going to lie. I know every time I say something, I know I'll get that TGL coming firing back at me. Perfect. But how many would agree then that knowing those numbers roughly will help? Knowing heart rate will help. Knowing that pressure drops as you go through the body, but just know from systolic output of the heart to diastolic when you come back in, it's got to drop from 110-ish to 70-ish or 120-ish to 80-ish, something like that, which means it's going to drop the whole way because things always flow from high pressure to low pressure. So it's going to be 105 at some point, 100, 95, 90, 85, and so forth. So hopefully that helps. Yeah, the chapter is, and this is the one thing, the bio book, the person who wrote it, I think, and I'm being as polite as possible, I believe one of the things that he had going on in his life was the need to always show how much he knew. And I think that carried over into the book, and there's some things that are just a little bit too much. Volume over time, not a bad thing to know. Yeah, I mean, you should know, like, things you definitely have to know. What exactly is cardiac output? I mean, that's definitely a fair game term. What's cardiac output? Not numerically, but what does it measure? How many learned is volume per minute, liters per minute? And how many learned that heart rate times stroke volume? Does that sound familiar? That cardiac output is your stroke volume, how much blood is squeezed out in a given compression, times how often the compression happens. Heart rate times stroke volume, definitely. But how many also learned Poiseuille's law, we'll talk about in fluids, where the volume flow rate depends on the pressure difference, but also viscosity of the pipe and the dimensions, length and width of the pipe. Perfect. So you should be able to make some reasonable conclusion that the fastest blood, the greatest volume flow rate is going to be found in the aorta or the capillaries. That one should be, like, those sorts of things. You should be able to just instantly make those decisions. So where do you have a greater amount of blood moving and where is it going faster? Two individual questions. So where does blood flow faster? So the actual red blood cells, if you could trace their speed faster than the aorta, exactly. They go incredibly fast through the aorta. They slow down in the capillaries. Why? Exactly. Need time to change things. Yeah, and also, also physically the size. The red blood cell is going to scrape against the walls far more often in the capillaries than it is in the aorta. Definitely true. So friction, wall friction. I think we call it the barrier layer or the boundary layer. Excuse me. So definitely part of it. But also from a practical standpoint, do you want blood to blow through the capillaries fast or go slow? Slow, because you want to get that gas exchange. You want to have nutrients go into the cells. You want waste to come out of the cells. You have to have time to do it. But as far as the total amount of volume moving through, so even though blood is moving faster in the aorta, is there more blood moving through the aorta in a given amount of time, or more blood moving through the capillaries in a given amount of time? Capillaries. Why? Because there is so much to them, and the sum of all the capillaries, all your capillaries combined, add up to a bigger cross-sectional area, as you mentioned, than the aorta. So if you were to put all your capillaries together at once, their radius, their diameter, their size would be greater than the aorta. And so as a pipe gets wider, something called the continuity equation. Yep, exactly. AV, you nailed it right there. So AV, as area goes up, velocity of the particles goes down, but then Q, the total volume flow rate. So hopefully this seems okay. Yeah. So after all things went off on that, don't memorize the details, but know the certain little nuances of where it's faster, where it's slower, and then recognize reasonable numbers. And I mean, things that you would pop up in a typical physio class. But yeah, the bio book is over the top. And I want to be careful speaking about that. I will definitely say in the physics chem books, I put some totally over the top tables in there, not to memorize, not to know all the details, but to look at and see a trend. And so if there is a scary table, just quick survey. For anybody who's taking the MCAT, did you get any scary tables on your actual test? Did anybody sit there and go, dang, this kind of overwhelms me? Yes. So you didn't have to memorize anything, but you had to work your way through very intimidating, daunting, massive tables. Yep, and most of it is just white noise, just filler. And you have to recognize what matters and what doesn't. So there is utility in seeing an overwhelming table, but it's not that you should memorize, not should know all the details, but instead be able to pick out what's important and be able to see a trend. Oh man, I don't know if I could actually answer that question. I would go by this guiding light, and that is, if you remember, if it sounds familiar from school and they said it a lot, then you probably should know it. If you had one obscure thing mentioned by a professor or a TA, or you read about in some article just one time in your life, probably don't know it. But the thing is, every test writer, the reason I say it's a hard question to answer, every test writer is a little bit different. So one test writer might think that it's really common to know certain PKs. Another one might think that's totally trivial knowledge. So err on the side of knowing a little bit more. If it popped up in a class more than once, know it. Just take the time to understand it and know it, but don't overdo it. Okay, so you don't really have that. Okay, yeah, you need that perspective. Then what I would ask, out of the kindness of other people's hearts, anybody wants to chime in and say, yeah, you know what? I did have to know that, or I didn't have to know that. And as you start seeing the trend in what other people had to know, that hopefully will give you some hint. But I will say the more you know, the better, up to the point where you start stressing about knowing like more. So it's a weird fine line between it. You want to know as much as you can, but the minute you go overboard, you're wasting time. I've not helped at all with that sentence, have I? So know a lot, but don't know too much, but know everything, but know some of it. But don't do everything, but just some, but not all. But do it, but not really. So if I helped, hopefully I've explained it, but Yeah. So what's listed up there, I really want to reiterate. So everybody read Jonathan's comment there. The number one reason people get burned on the MCAT is that they're trying to know everything and they don't take the time to apply things. And just, I mean, I literally had been in an email exchange with somebody over the last like week when they got their score back, just devastated. And listening to everything they did to study, and they had 3 book sets and they read them all. They watched all the con videos. They had read and reviewed everything to review, and the score didn't go well. What would you tell them? What went wrong? Doesn't mean a thing if you can't apply it. Questions, more practice, all that. I mean, you got to just do that. Did you practice? And I'm telling you, it's so painful. If you've been on the other end of this, advising somebody who worked literally, she studied, I think, 9 months, 10 months total, and felt so confident going in and just got devastated. And it came down to, I started asking, did you do these double AMC things? No. Did you finish phase 2 and 3? No. It is so sad. It's the hardest part of this job by far, because this woman is so sweet and so smart, but put too many eggs in the I got to learn everything basket. She'll do fine next time. I'll bet you anything she's going to have a great score next time. Yeah. Oh, everybody reads Fabiana's message. That is so true. Know as much as you can, but how many have just gotten old enough in life to realize I can't learn everything, but what I can learn really well and figure it out as I go. Yep, active recall. That's what you need. You have to be able to recognize things in weird situations. Know your graph from biochem when it applies to GChem. Know things out of context and you will do great. Okay. So I want to get into one thing. I hope this structure, I drew it and I realized it just doesn't look good from this angle. Artistically, it's not right. But how many recognize hemoglobin has something iron in the middle? You have the heme, the porphyrin ring, this planar system in this plane. You have O2 bound above. And O2, it's at an angle because this is sp2 hybridized. It's actually kind of sp2, sp3 because of resonance. But you have about a 109 bond angle. And how many learn you have histidine connected to another protein? So many have learned that this is basically what you have around iron in hemoglobin. Yeah, I totally agree with that. So notes are one of the most overrated things you'll do. Notes after homework are awesome. That's where I think you should be taking the most notes. But even going over a recording, let's say hypothetically, maybe a lecture, you could find a lecture that had been recorded. Even taking notes on that, you're still not paying as much attention. Best thing you do is try to figure out what the next question is going to be. So when you see something like this, your mind should immediately scan, is that right? Histidine, proximal, distal, O2, bent angle. How does it release? O2 binding curve. Start thinking how things apply. So how many have learned somewhere along the line that there's some O2 binding curve like this? So this O2, saturation, this is pH. This is like 7.2, this is 7.4. How many have definitely learned this curve somewhere along the line? So according to this, is O2 bound more at 7.4 or 7.2? 7.4. At 7.2, you lower the pH, you get a little more acid. So let's say that acid appears. It's going to appear everywhere, but if it appears here, it's going to bind the protein. When it binds the protein, this actually denatures it. The protein sort of collapses into here, and it forces the porphyrin ring up. The porphyrin ring used to be planar. Now the porphyrin ring is sticking above the iron. Is this O now in the way? Is this porphyrin ring now hitting the O2? The O2 gets pushed up and released. So the so-called inactive form has 5 ligands. It's trigonal square-based pyramid, not trigonal, I'm sorry, square-based pyramidal. Whereas before it was known as octahedral, had 6 ligands. So how many have learned that? The active and inactive form? +2 and +3 forms. I mean, they use different words. But when at low enough pH, this goes up, pushes the O2 off, and O2 gets released. So lowering the pH releases O2. I hope this is structurally makes some sense. Real quickly, why is carbon monoxide so bad for you? Oh, that's such a terrible drawing. Let me redraw it a little bit better. Why is carbon monoxide so bad? High binding affinity. Why? It's sp hybridized, so it binds in a straight line. So when the porphyrin ring raises up, does it bump into the CO or no? So steric hindrance is kicking the O2 off. When the porphyrin ring goes up, knocks the O2 off, so O2 releases, but carbon monoxide stays on because even when this ring goes up, it doesn't push it off, it doesn't bump into it. So CO has a much higher binding affinity. And weird question, off on a tangent, but what color does blood turn if somebody has carbon monoxide poisoning? For anybody who's a first responder, they probably taught this to you. Like you walk in, let's say somebody has a fireplace going, bright red. Their lips and their tongue turn cherry red. That's so weird. Would that mean their blood is heavily oxygenated or deoxygenated? Because how many would have predicted blue? First thought would have been blue and ends up cherry red, and here's the reason why. The issue with carbon monoxide blood, how many learned a cascade effect that there's actually 4 hemes within the hemoglobin? How many learned that there's 4 irons altogether, 4 binding sites? And then how many learned something about cooperativity? I think I eked the word out barely, but how many learned when one goes on, denatures next one, so another one go on, another one, another one? And then how many also learned when one gets released, it helps the other ones get released? I'll start with a painful one. But what happens if you have a carbon monoxide on here, it doesn't start the cascade effect. So if one of these has carbon monoxide, it doesn't denature enough to help the 2nd, 3rd, and 4th release. So it's kind of weird, but your heme then has 1 CO and the 3 O2s never release. So the problem with this patient isn't that they aren't getting enough O2. There is blood that has all the O2 you could ever want on it. But does the O2 release? So you have worthless red blood cells that are carrying around 1 carbon monoxide and 3 O2s that as it travels around cannot release that O2. So it's like having all the money in the world, but you can't spend it. All the O2 you could ever want, but you can't release it, can't get to it. So their blood actually stays fully oxygenated and the heme doesn't release the O2. So does that make sense? That's why it's red, because of that cascade effect. It doesn't release it. Hopefully seems okay. And then question, how many learned that at some point as a first responder class or biochem class or physio class? Okay, one last thought and I'll move on back to chem where I belong. But once upon a time in a land far away called maybe a previous MCAT, they might have talked about a genetic disorder. I'm going to put a family name up here, but if you look up Fugate, inbreeding, Kentucky, anything like that, you're going to see a picture pop up on the internet if you type this in of somebody that totally looks like a cartoon character. They've been colorized. There's no colorization in that picture. Those are really what they are. Blue people, the blue-skinned people of Kentucky. It's a completely inbred disease, genetically inbred, and so Appalachians, I guess apparently this is where it was quite prevalent. But it's a disorder where their hemes are permanently denatured, so they do or do not take on O2. So is it like carbon monoxide or is it complete opposite? If their blood is blue, so the red blood has a blue tint, their blue blood is definitely blue. So they start taking on a blue tint, and then as these cells, or as they die out, they accumulate some blue as well. That's also part of it. But I have no idea how to pronounce it, so I'm just going to make it up as I go along. But mesoanemia is what the disorder they get. What does anemia part mean? cannot transfer O2. Exactly. Shortage of O2. So it's an anemic condition. At rest, probably not a big deal, but highly unlikely any of that family would ever be long distance runners or endurance, because they're going to end up having a hard time catching up to their O2 needs. Okay. For what it's worth, the reason I bring this up, how many actually did search on the internet and came up with like Papa Smurf, picture of the patriarch? Yeah. He ended up passing away, I don't know, maybe 10 years ago. I sort of lost it. Oh, you got so into it, got totally distracted. It happens, but this is on purpose. So when you look this guy up, he passed away. And when he did, that became an interesting news. And chances are a test writer was watching news and said, hey, that's curiosity. And they wrote an MCAT passage about it. How many can see that actually happening? Things that are common becoming MCAT passage topics. Completely true. I hope that you start paying attention to what's going on. So right now, our vaccines, COVID, mRNA, all those other things, know a little bit about it. When cloning was really big, I mean, this was 20 years ago when Dolly, that sheep, died. That was on there. When AIDS, there were passages on retroviruses. When these things become trendy, passages start to take them on. So I will bet you the sociology aspects, COVID will be on there. It has been a little bit, but I'm assuming it'll be more and more as they study it more and more, the socioeconomic impact. So COVID is trendy. And just feedback, how many had some sort of like viral load, immunization, any of those type of passages when you took the MCAT last year? Anybody took last year, did you notice that you got one or two? Was that topic seemingly a little more tested than what you would expect from school or what we would have ever told you? So know everyday things from a year ago when the test was probably being written. So COVID was a huge factor for sociology and for biology. So the point being, knowing about the Fugate family was awesome 10 years ago. Probably not as helpful for your test today. Yep, go find the old guy in the newspaper. That's a little bit of stalkerish, but it'll definitely work. Good luck with that. Good luck on the space travel. I'll get back to me on that one. Sorry, I fat thumbed it and moved on to the question. RNA vaccines, yes. And did somebody recently win a Nobel Prize for that technology? Yes. So probably good idea to know how those work. Just a hunch. Okay. Somebody asked what kind of questions would you get, and I sort of blew you off and held it at bay, and now here it is popping up. Is this a reasonable question that would show up on the MCAT? Is this, for anybody who's taking the MCAT, is this kind of thing like, oh, damn, I might have even had that question? They love this sort of thing. Knowledge-based questions that you apply. So getting the pH of something. I'm going to go through the math of this slowly and methodically. I want you to just see the beginning and end and learn how to BS your way through it. Okay, so I have this. When I multiply numbers, what do I do with their logs? Just like when I multiply numbers, what do I do with their exponents? Perfect, add them. Yeah, good question. I'm gonna actually, do you mind if I toss your question out to everybody? Because for me, I'm that person who I hit something in the internet and I read until I find an article. And so I sometimes will go to somewhere called PubMed, so public journal articles for medicine. And I like reading through those things. But oftentimes, unless you get the full article or you're totally into it, you just get pieces of it. Anybody have any suggestions where you pick these things up? How many are PubMed people as well? Yeah, so PubMed's just great for that. That's my first knee-jerk response. But what is Scholar? Uh, oh, Pub and Bed. Forget the Pub and Med. Yeah, close enough. One letter. A Google Scholar. Okay. And would one of you mind answering that on Discord? Because that's going to help lots of people if you don't mind. And sorry to pass the buck, because all I could add in from my perspective is PubMed's my favorite. Yeah, in Google search, I think is just pretty much our standard thing, but then it's picking the right article. Oh, JAMA, and even on top of JAMA, they have the JAMA newsletter. The newsletter is really good, especially before you go on a med school interview, because everybody reads it. Yeah, and yeah, I would definitely buy into JAMA. Although for the MCAT, the articles might be a little bit better because they're more traditionally article-like, but still, hope that's a good call. I like that one. JAMA is a good way to go. Okay, back to this log of 10 to a power. Don't fight the power, just bring it down. And by the way, I despise when people do derivations, but there's a method to my madness. Negative negative means this is going to equal 5 minus log 1.2. So I want you to notice something. Did this number go down there, and did this number end up here? I mean, I did all the log rules I'm supposed to, but if I followed all the math rules, is this always going to happen? Definitely a trick in the book that definitely pushing on you to do. So if I want to do negative log of 6 times 10 to the minus 8, that's 8 minus log 6. Minus log of 4.17 times 10 to the minus 11 is 11 minus log 4.17. It introduces a problem of guessing what the log is, but at least that's a starting point. So for this one, I'm going to say, no, a couple logs. 2, 3, 5, and 7, your prime numbers, and it works out kind of easily. Take this 3, move it here, this 5, move it there, that 7, move there, meaning I'm going to repeat my 3, 5, 7. So log of 2 equals 3, log of 3 equals 5, log of 5 equals 7, log of 7 equals. I'm going to have to add something in here. I'm going to put a dot. So it's a little bit easier to memorize, but if you memorize these prime numbers, you can deduce every other number. But log of 2, so the prime numbers are 2, 3, 5, and 7. Log of 2, 3 is the next one up, so 0.3. Log of 3, 5 is the next one up, 0.5. Log of 5, 7 is the next one up, 0.7, and 0.8 and 4. So how many are okay and you think you could memorize those numbers or practice enough with them that they pop up? So does anybody feel okay with that? Sure, with practice. Okay. Did you need that on this question? Do you need to be that precise? Nope. All you needed on this one is a little less than 5. So sorry that my little less is so poorly written. So a little less than 5, meaning I got to know some things about the body. So somebody said get rid of A and B. Why are you getting rid of A and B? What's pH in the small intestine? Neutral. We absorb things there. We want to absorb from a neutral environment. Pancreas. Is the pancreas responsible for generating basic fluids that are released through the or into the duodenum through the pyloric sphincter? So it's going to be slightly basic. Lysosomes, anytime you see lice, things break. Do we typically break things under acidic or basic conditions? acidic. So how many know that lysosomes are slightly acidic? The stomach is acidic. Stomach is around 2-ish. Lysosomes around 5-ish. How many are okay with this answer? And again, for anybody taking the MCAT, how many agree, dang, that's exactly the kind of crap they like to do? Math that isn't precise, you just have to be close enough and then apply it. Yes, and here's why you have to know it. You should know that at least the small intestine, do things get absorbed in the small intestine? Well, do things get absorbed from the intestine in general, but small intestine in particular? Is this true? Do we absorb anything in our small intestine? Can't remember. Definitely. And blood needs to carry neutral or charged species, generally speaking. It can carry both, but to absorb, to pass through these pathways, neutral. So typically the small intestine has been neutralized. That's why when the gastric fluids pass through the pyloric sphincter, they get neutralized by bile salts, by basic salts. Yeah, and I'm counting on the fact that all these things, when you do the GI lecture with Spencer, Spencer is going to be really solid in the things you know. But also, even though you've never taken the class, I've never taken physio either. But as I learn little things in like tidbits here and there and test it with my real body, I don't know about you, but have any of you ever thrown up? I have. And when I do, it burns, yet it's not fire. So, okay, so you knew the stomach's acidic. Okay, that's fine. But when you release waste through other portals, does it burn? Way too personal question. I do apologize, but being pragmatic about it, how many would agree when you release waste, it doesn't burn anymore? Yeah, depends on what you've eaten beforehand, but in general, can you basically say it's been neutralized? So acidic fluids from the stomach had to be neutralized by something. How many learned the liver, gallbladder, pancreas, they're all involved in either formation, transport, storage, somehow they're involved in the basic materials? I have no idea how basic they are, but I know they're rich in bicarb, so they're going to neutralize things. And so I guess my best advice is pick up pieces as you go and cling to whatever you can in terms of what you know. But lysosomes, we break things down in acidic environment. And if it's the first time you're seeing this stuff, take an extra moment to write it down as a little like, oh yeah, note. Okay, one more question. So if you want to click on this page, I think weird things are going to happen in just a second. So 3, 2, 1. Let me get rid of all my writing. 3, 2, 1. Gone. So it's around 5-ish. So pH of 5. So just under 5, that was our conclusion. Small intestine is around 7. Should be a little bit, pancreas should be a little bit more than 7, slightly higher, just barely higher. Lysosomes around 5-ish. Stomach, we know, is extremely acidic, around 2. So from those of you who've taken physiology, are all 4 of these reasonable things that have shown up as common knowledge? The intestine, lysosomes are slightly acidic, gastric fluids, highly acidic, and the pancreas is part of the things that neutralize. So again, it's a GChem lecture, but it's a GChem lecture applied to physiology, well, just bio in general. So hopefully these things seem okay. So clicking in 3, 2, 1, and for this one. So which of the following compounds is likely present in an alkaline solution? All right, so people are telling me what it is. What is it definitely not? Unfortunately, that's how I have to answer these things. What does alkaline mean? Alkaline means basic, perfect, and you're saying can't be A, can't be D. I'll agree with that, because a couple things you should know. Metals generally tend to make bases. So I'm going to make a little note here. Metal oxides and hydroxides are basic. Non-metal oxides, and I'm being lazy and not writing hydroxides, but oxides, when you make them wet, become hydroxides. So this is a non-metal, this is a non-metal, this is a metal, and this is a question mark. Okay, so just that trend. So I want to do the periodic table real quickly. Just to let you know, the periodic table can be an absolute bear. If you let it. The periodic table can be an absolute bear. Basicity goes up when you get more metallic. Metal oxides are basic. Electronegativity increases when you go in this direction. Acidity increases when you go that way. Radius increases when you go that way. Periodic table can be an absolute bear. Okay, so I'm going to get rid of these two right away because, just as you said, acidic and acidic. Okay, question I got private sent to me by a couple of different people. Oh, R stands for radius, so atomic radius. So in return, you must answer, what does E stand for? Electronegativity, perfect. Okay, so it's a real bear. Basicity, electronegativity, acidity, radius. So I kind of like that one. Students showed me that years ago, and I went, dang, that's pretty good. So I've stolen it from somebody I don't know. I don't know what teacher taught them that, but good call. My question, isn't OH basic? I mean, most people are going with that one. It seems really tempting. So I'm going to just draw this out. And from an OChem standpoint, you tell me if I've just made OChem professors happy or sad by saying OH is a great leaving group, going to come off as OH minus and leave a primary carbocation. Uh-oh. Are there some O-chemists in the crowd that I've just pissed off? You have to protonate it, make it into water. Urgh. Like that. Ends up, that one isn't. So what are the odds, whoever wrote this originally, and I stole from, and changed a few things to look like I didn't steal, did that, put an OH on an alkyl group so that people zeroed on the OH. Quicker, faster, better way to recognize bases. There's always going to be a few exceptions, but in general, bases, metal oxides, acidic compounds, non-metal oxides. So if I start looking at these compounds, H3PO4, SO2, N2O5, H2CO3. How many agree acidic because non-metal, 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 non-metal? Does that sound believable to you? On the other end of the spectrum, K2O, NaOH, magnesium oxide, calcium hydroxide. Acidic or basic? Basic, perfect. Quickly just want to mention where this passage was inspired by. The sky is rich in CO2 and a little bit of other non-metal impurities. And the soil, if you want minerals, you dig into the ground, you find minerals. So generally speaking, the sky is slightly acidic. Natural rain should have a pH of around 5.5 to 6, depending on where you live. The soil, the dirt, naturally is around 7.5, 8-ish, depending on where you live. But is there a little region of space where the air meets the soil, called the topsoil? Is there a little bit of topsoil that gets aerated, interacts with the sky? So if you mix an acid and a base, can you make topsoil that's essentially neutral? Sure. And depending on the natural pH of that soil, will that dictate what type of plants will thrive there? So number one, do fertilizers sometimes change the pH of this soil? Sure, there's specific fertilizers designed to raise or lower the pH of soil. Ammonium nitrates are pretty common when you want to make it more acidic. Potash, potassium oxide, pretty common when we make it more basic. But more importantly, do different plants thrive at different conditions? So for instance, if I found a cactus, tell me about a cactus. Does it grow in an area with lots of rain or very little rain? Very little rain. So it ends up, a cactus then is probably growing in soil that's a little more basic. So if I told you the enzymes involved in nutrient transport in a cactus had, let's say, natural occurring optimal pHs, pKs, and so forth around 6, 7, or 8, which one would you believe? For cactus? So a cactus thrives in an environment that's slightly basic, so close to 8, perfect. If I told you mosses or things growing in a rainforest, that their optimal pH for their nutrient transport was around 8, 7, or 6, you would say 6. Perfect. How many agree this kind of makes sense? You probably never think about it unless the few of you are from the Berkeley area and you grow pot in your closet. Maybe you do, but everybody else? I'm so sorry. That was so wrong and inappropriate, but just sometimes can't help yourself with the wrong things. But at any rate, short of somebody who's a freelance indoor horticulturalist, these are weird topics, but these are the kind of things they like to ask. Can you apply it? So I'm hopeful that these things make some semblance of sense. So yep, the right answer, the metal oxide. Metals equal basic, non-metals equal acidic. Kind of zeroing on that, and makes identifying things a little bit easier. I'm going to erase everything I've written here so that my words can come in. So if you want to screenshot it, 3, 2, 1, and clear. So strong acid, non-metal oxide, it's out. Non-metal oxide again. And notice I call them both non-metal oxides when in fact, I really should call this a non-metal hydroxide because it's got the H on it. Non-metal oxide is just O. But non-metal hydroxide and oxide, I'm going to use the two terms completely interchangeably, even though I shouldn't, because the non-metal is what matters. Metal makes it basic. This makes it neutral. So alcohols generally around neutral or so. So presence of a metal creates a base. You can also think about it. Can you replace a lithiums with H? So is there such a thing as H2CO3? You bet. So lithiums, get rid of lithium, except an H plus in its place. This compound then is an H plus receptor. It's a proton acceptor, which makes it a basic compound. Okay. The next thing, this is in your handout. I'm going to blow through this kind of quickly because this is your rote memorization, but equilibrium constants, products over reactants. Why is water not in there? Why am I missing my water? Pure liquids. Pure liquids and pure solids, their concentrations don't fluctuate much, so you don't bother putting them in. Already accounted for. Ka is products over reactants numerically, but pKa, negative log, is just a way to make the number more convenient for me to describe. So let's play this game. My Ka equals 7.03 times 10 to the minus fifth. What is the pKa? You have 10 seconds. Between 4 and 5, perfect. So it's about 5 minus log 7, 5 minus 0.84, 4.16. Okay. If you got between 4 and 5, closer to 4, you did exactly what you needed to do on this. So we're deep. We're in good enough shape. Okay, I'm erasing this. 3, 2, 1, gone. Note, as an acid gets stronger, it dissociates more. It dissociates more, bigger numerator, smaller denominator. So Ka goes up. So its acid strength goes up, Ka goes up, because negative log pK goes down. So how many have learned that? Lower pK means stronger acid. Just one of those things, you got to program that into your mind. That's one of those things that goes so far beyond memorization. That's just flat out know it. It might be mentioned once or twice or 4 million times in the book. Maybe it's mentioned. Base hydrolysis. Dissociation implies the acid breaks up, HA and A minus, but hydrolysis implies what's breaking up, the base or water. So hydrolysis, water is going to be involved in the breaking in this case. So A minus, the conjugate base, is going to come and take an H from water, making HA and breaking the H2O into H plus and OH minus, keeping the H plus for itself. Same thing, products or reactants. But here's how these two relate, kind of a connection I need to worry about. And that is, as an acid gets stronger, as HA is stronger, it's going to push more in the forward direction. Does that imply the base is stronger or weaker? So if it's strong going forward, does that mean it's weak coming backwards? So if it favors the forward, it's going to be less coming back. If it favors the back, less going forward. So would you agree only one of these two can be stronger than the other? Only one can push it. So if the acid is strong, does that mean the base is strong or the base is weak? Perfect, it's weak. So if stronger the conjugate acid, the weaker the conjugate base. Sure, this sounds familiar, but just want to really make sure it makes sense. But now I want to connect everything. As an acid gets stronger, its conjugate base gets weaker. As the Ka gets larger, the Kb goes down because they multiply to 10 to the minus 14. And then if pK goes down, pKb goes up. I'm assuming these are things you know, but just want to make sure here's your overall relationship. And again, how many answer choices on the MCAT? 4. Perfect. How many different ways to say the same thing? 6. Is this a test writer's dream where I can write all sorts of multiple choice questions and screw with you like nobody's business and still have leftover ways to mess with you on a future question? Have to be able to say the same thing multiple ways and then recognize when you're saying the same thing or opposing things with different words. Okay, the other thing you have to know, pH plus P or pK plus pKb equals 14. Oh, yeah. How many see Jonathan's question in the chat box and just want to kick him in the shin? All following are true. 1 and 2, 1 and 3 only, 3 and 4. Oh, you are truly bringing happiness to the whole realm here. So thank you. Moving on then, screenshot if you will. And how many don't even bother screenshotting because it's all in the handout? And I hope some of you are starting to master the art of notability and move things around and like modify it into what you need. But let's see how this one goes. You have 15 seconds. Yeah, the other one is right. What the heck does higher ionization constant mean? Good job on the speedy answer. Higher ionization constant means it ionizes more, meaning it breaks apart or stays together more. Breaks apart more, higher ionization constant. So higher, more ionization, more breaking apart, which would make it more acidic or less acidic. Assuming it's an acid, and I don't know for sure from the question, but I'm going to go with that because I see pK in one and I see acid in another as far as answer choices. And I'm going to go with the theme that's probably acidity. Ionizes more, stronger acid. What does greater dissociation mean? More ionization. How many agree it's the exact same thing? Breaks into more ions? Is it the exact same thing we just did in choice A? Are they essentially saying the same thing, which means keep them both or get rid of them both? Get rid of them both. They're both gone. More electrolytic acid means it breaks into electrolytes more, it dissociates more. That is saying the exact same thing. Wow, an increased pKa means what? Weaker acid. Perfect. Associates less. Weaker acid. I'm so impressed. For the people who tossed answers out there, and a few of you did, all of you nailed this one in a very timely fashion. So again, you're obviously not going to see this as your exact question on the MCAT, but the more you can start taking advantage of answer choices, using information and answer choices, the better you're going to be at taking this test. You can answer a question from this part or this part, but if you can do both, you're going to be a better test taker. So how many see the utility? How many know it's there, but how many just can see the utility on questions like this, where you really can start pitting answers against one another a little bit? So process elimination is huge. So is matching things. Those are skills. On a multiple choice test, you have to treat it differently than fill in the blank. Deduction is important. Memorization helps, but deduction is probably more important. Okay. A, B, and C are all complementary. D is the opposite. So clicking in a couple seconds here. 3, 2, 1. And on we go. Again, this is something straight out of the handout, so I'm going to click to get it up there quick. And then once everything's in, I'll take a second to go through it. Okay, so I want to stop at this point and just summarize what we have. How many learned in GChem a strong acid fully dissociates? Put it in water and it fully dissociates. You get complete separation of H+ and conjugate. How many learned a weak acid partially dissociates? So it doesn't fully dissociate. That's GChem. But because I'm doing GChem, OChem, biochem, and physiology, all of this, I have to be a little more comprehensive. So I'm going to add a third category, something that's so weak that when you put it in water, you don't even notice it. So I'm going to agree, if you put CH4 in the water, its pK is so ridiculously high, there's no way it's going to dissociate. So it's essentially neutral. So inert or neutral would be this category, but I'm still going to refer to it as a very weak acid, something that associates less in water. So in an aqueous environment, we don't notice it at all. Okay, so strong acids, weak acids, and essentially neutral. Strong base, weak base, and essentially neutral. But here's how the conjugate pairs work out. HCl is the acid, Cl- is the conjugate. If this is -7, you read this one must be 21 because they add to 14. CH4, 49, so CH3- must be -35 because they add to 14. Carboxylic acid, I'm going to choose acetic acid around 4.7, so acetate's 9.3 for the pKb. It ends up kind of weird that they're just, I don't know, 9.3 and 4.7. It's just coincidental, but ammonium is like 9.26, rounds to 9.3, so 4.7, conjugate pair. The rule is going to be this. When the pK is between 0 and 14, it's weak. When the pK is negative, it's strong. pK is above 14, it's essentially neutral or inert. It's so weak, we don't notice it. So if this is between 0 and 14, and this is between 0 and 14, I have a weird sort of phenomenon that's going to happen. So first, let me identify one thing I think we've been told enough times, and that is, as the acid gets weaker, its conjugate base gets stronger. How many of you definitely learned that at some point? The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger its conjugate base. Pretty much, they pound that into you in GChem, and they never stop beating that into you through the rest of your chemistry experience. But I want to go one step further. How many have learned strong acids have very weak conjugate bases? Strong bases have very weak conjugate acids. Definitely that's something I remember being told in GChem. But here's what they never told me directly. I had to get it indirectly. The conjugate of a strong acid is very weak for the base. The conjugate of a strong base is a very weak acid. But the conjugate of a weak acid is a weak base. How many reading this, does that sound weird? How many, when you read this, that does not sound right? Something sounds off. And the reason it sounds off is because they didn't word it that way. The sentence they probably told you was a little bit different. How many were told that if you take a weak acid and mix it with its weak conjugate base, that you get a blank? I take a weak acid and mix roughly equal concentration of its conjugate base, I'll get what type of solution? Ah, perfect. Buffer. Exactly. How many learned that a buffer is a mixture of a weak acid and weak conjugate base? Weak acid and weak conjugate base. Is that something you've definitely learned in your travels? We did the Henderson-Hausbach equation earlier, but this is one that we apply to it. It's a weak acid and weak conjugate base, both in solution. Buffers, they resist drastic pH change. They will have small fluctuations in pH, but generally it stays relatively constant. So if I add acid, there's a base in it to consume it. If I add base, there's an acid to consume it. They consist of weak acid, weak base in roughly equal proportions. So know then, acid gets weaker, conjugate base gets stronger, strong goes with very weak, strong goes with very weak, but if they're both weak, then you can form a buffer. No, isn't that weird? So nobody ever said that. We just assumed it because we assumed strong acids have very weak conjugate bases, but it doesn't mean weak base always has a strong acid. A very weak base does, but a weak base, anything between 0 and 14, actually has a weak conjugate acid. It just doesn't sound right. It sounds weird and odd, but it's totally true. So it isn't always true. It ends up you have a buffer. But would you agree something does not sound right in that sentence? Strong goes with weak for sure, but weak doesn't necessarily go with strong. It just doesn't sound right because nobody ever took the time in chemistry to say it. They just said, oh, by the way, strong goes with weak, strong goes with weak, but if you mix two weaks, you get a buffer. They've definitely said all three of those sentences, but never took the time to distinguish like this. So very weak will be strong, very weak will be strong. But if it's somewhere in the middle, just weak acid, it's conjugated to weak base and vice versa. And you end up getting a buffer. Okay, screenshot time if you want. 3, 2, 1. Typical strong acids. This is just pure memorization. HCl, H2SO4, the first proton, not the second, and HNO3. Got to know it. Here's the H with a halogen. So is there a class of compound known as the halo acid? Is that something you've ever heard of before? We have an acid and a halogen. Sure. And here you have an H on an O, H on an O. These are sometimes known as oxyacids. Again, notice the presence of nonmetals and nonmetals, nonmetal oxides, nonmetals, but again, halo acids, oxyacids. This is where OChem is going to pop its head into our otherwise GChem physiology lecture, and that is seeing a trend. For the halo acids, as I go down a column in the periodic table, there are a couple things you would note. Number one, does the halogen get larger or smaller as I go down the column, the periodic table? As we go down a column, things get larger, perfect. And do they get more or less electronegative as I go down? Less electronegative. So two ways of thinking about it. Number one, larger, so weaker bond, it breaks more easily. Or number two, less electronegative, so it's going to pull. Which one do I do for down a column? Electronegativity or size? This becomes important because both of them, those two trends are going to start contradicting one another. And this is one of those really important things that maybe you just do instinctively but don't really think about it. But when I go across or down, what do I do? Actually, let me rewrite this. I want to write it like Scrabble. When I go down a column, I worry about size. When I go across, I worry about electroneg. Sorry, I ran out of room. So down a column, size is a more important feature. So size is going to go down, exactly. So bigger atom is going to affect the acidity, not the electronegativity. When I go across, I worry about electronegativity. Okay, so with that in mind, let me give you the side chains of 2 amino acids, and you tell me if I've done this right. Oxygen is directly above sulfur. 14.5 for the pK of serine, 8.4 for the side chain pK of cysteine. Have I gotten it right, or am I lying to you again? So as I go down a column, S is bigger than O. Longer bond makes a weaker or stronger bond. So longer bond, weaker. Weaker means it breaks more or breaks less. Breaks more, so therefore it makes it more or less acidic. More acidic. So HF is the weakest, HI is the strongest acid. So as you down a column, acids get stronger, which means which is going to be stronger, OH or SH, in terms of acidity of the side chain. SH is going to be stronger because it's lower in the column. Stronger would mean a higher or lower pKa. Lower pKa, exactly. So cysteine has lower pKa than serine. So lo and behold, every now and then, Todd's going to tell the truth. Todd's going to tell truth. Every now and then it happens. So take that. Okay, hopefully good on this one. I'm going to erase because I need room for everything coming in. So erasing in 3, 2, 1. Yeah, exactly. So everybody, Stephanie put, because Stephanie's going to take away that question mark and put an exclamation point because she totally got that. That's, you're spot on. That's exactly what it is. So again, sorry to do this, but why did you put a question mark and not an exclamation point? Did you know it? Yeah, just a question mark was a typo. You accidentally hit question mark instead of exclamation point. And that's part of it. And I don't mean to single you out because I'm basically hopefully singling all of you out. Everybody's guilty of this. But how many lose confidence in spurts and instead of saying it's true, you say, I think it's true. Is this possible? Is this true? It's who we are. Come test time, can't afford that insecurity. Boldly make your statements, and yeah, you're going to be wrong every now and then, but you're going to be right way, way, way more often. Okay, so increasing atomic radius means increasing acidity. Two ways of looking at it. The bigger the anion, the more it stabilizes it and pulls it forward. Or the bigger the anion, the longer the bond, the more it can break and go forward. But for oxyacids, this is true. And somebody brought it up. HF is a weak acid or strong acid? Yep, it is. No question marks allowed. No. So you knew it. Trust you knew it. That sentence came out weird, but anyway, yep, this is a weak acid. Strong, strong, and strong. Perfect. Okay, haloacids, done. Oxyacids. Uh-oh, my screen is lagging behind. So somewhere along the line, you possibly learned that resonance affects acidity. Who might have heard something crazy like that in OChem? Maybe once or twice, I might have mentioned it. So here's the rules. If I have one bond to O, one withdrawing group, but if I have two, is that going to make it more acidic or less acidic with two pi bonds to pull electron density away? More acidic, perfect. So because it makes it more acidic, this is my most acidic, so ends up resonance is most important. Because I'm doing this in GChem, we don't use the word resonance. OChem people will be really angry. So instead we talk about oxidation state. The more oxidized, the more bonds O, i.e. pi bonds O, the more acidic the compound. So +6 oxidation state, more acidic than +4 oxidation states. If they're tied, which they both are, so let me just bring this up. So because there's 2 bonds O by resonance, this is more acidic. So this is my most acidic compound. These two I now have to decide. They have the same amount of resonance. They each have 2 pi bonds O. But the question is, which is more electronegative, S or C? Oh, Fonkelbrish. Oh, I was supposed to pop up when I said that. My thumb is yeah, I apologize because things are just, it's probably all going to come up at once. It's probably storing all my clicks. But what is Funkelrish? I'm going to write it in, and then hopefully the computer will catch up and put it in. The relative electronegativities. S is more electronegative than carbon. You're absolutely right. So that this is more acidic than that. Finally, it just kicked in. So because S is more electronegative than C, that's number 3. So number 1, number 2, and number 3 in terms of relative acidity. Does this sound an awful lot like OChem in the middle of your GChem lecture that we'd go over physiology? You bet. It all ties together. So a bunch of Funkelrish. So S is more electronegative than C. Okay, just blowing through those really quickly because those end up being, for whatever reason, one of the topics they like, halo acids and oxyacids. And again, note non-metals. Typical buffers, we've gone through this, and now I want to put it in different form. So we mentioned very first page, and I'm going to do those same compounds. Carboxylic acids, carboxyl terminal is around 2 to 3. Just run-of-the-mill generic carboxylic acids around 3 to 5. At a pH of 7.4, carboxylates are what we see. We use glutamate and aspartate, not glutamic acid and aspartic acid in the body. Amino terminal, 9 to 10. Typical mean around 9 to 11, really, really close. Physio form in this case, 7 is lower than these numbers, so physiologically. Amines end up protonated. Imines, the double bond ones, are neutral, but amines end up like this. This is one, again, I think you should definitely know. And so I want to mention this in venous blood and arterial blood. So in arterial blood, 7.4. In venous blood, it's 7.2. So help me out on the Henderson-Hasselbalch equation real quick. I'm going to put pK1 plus log of, I can't remember, is it base over acid or acid over base? If only I could remember that. It's log of base over acid. So in this case, the base is HCO3 minus, the acid is H2CO3. Okay, so with that in mind, I have 7.2 in venous blood, 6.4. So overall, do you agree this must equal a positive 0.8, which means I should have more of this than this? I know log of 7 is about 0.8, a little under. So it's like log of 6-ish or so. So with that in mind, 6 to 7, the ratio of bicarb to carbonic acid, how many learned it's about 6 to 1 or 6.5 to 1? So anybody learned about 95% or 85% is in this form, about 15% is this form? How many learned that the majority of the CO2 is transported as bicarb, about 85%-ish? Okay, and it comes back to that equation. Clearing in 3, 2, 1, done. And then why is phosphoric acid on this list? Is phosphoric acid actually in the body? Yes, we normally draw it like this. What does PI mean? Exactly, inorganic phosphate. How many learned inorganic phosphate as the chunk of ATP or ADP or whatever when you go in one direction or another, you spit out an inorganic phosphate when you go from ATP to ADP and vice versa? That thing you're spitting out is phosphoric acid residue. It's basically not the protonated form, but the deprotonated form. It's an equilibrium between these two. But overall, -1 and -2, so at 7.4, it's slightly more negative, about a 60-40 ratio. The reason this matters, the reason this is so critical, what is true of the charge of the DNA backbone? Is the DNA backbone neutral or negative? Negative. Whole bunch of ramifications from this. Number one, do phosphates then, if they're negative, want to be near each other, or they want to actually twist and try to get away from one another? They want to twist and get away from another. Exactly. So is DNA flat or helical? Forms helical structures. Also, it can't fold back on itself to form an H bond because that would form or force the phosphates too close together. So when it base pairs with itself or another strand in general. Helical, exactly, to get the phosphates away from each other, twist away from each other, and it has to base pair with another one. So phosphates internally don't repel one another. Okay, number two, when do electrophoresis, does it migrate to the anode or the cathode? When I do DNA or RNA, anions migrate to the anode because that dang phosphate backbone. ATP, because phosphates repel one another. Will ATP have longer or shorter phosphate bonds than just ordinary PO bond? Because there are a whole bunch of negative charges, they attract or repel in ATP. Exactly, they repel. So ATP has slightly longer, weaker bonds, which means when you break them, is it favorable? When you hydrolyze ATP, is it favorable and you release energy when you go from ATP to ADP? You're breaking a weak bond to form stronger bonds, which is overall exothermic. So ATP losing phosphates will release energy because of the repulsion, making a weaker bond. All that comes back to just this right here, meaning, will ATP and DNA work at low pH? If we're at pH 2 or so, would DNA be happy or denatured? Because all the phosphates would now be neutral. So ATP would not work, DNA would not fold at low enough pH. How many learn this? How many learn acid can denature DNA? I mean, hopefully it seems okay, but just, I don't know if I'm belaboring the point. Phosphate, this is slightly the more popular form. This is the equation. This is how you'll normally see it, but because it's per liter and per liter, liters can cancel, so could I also do just moles? So if I wanted to be lazy and just put 0.2 molar over 0.1 molar, could I just do 1 over 2? As long as I keep the right ratio? Yes, be lazy. A buffer pH is said to be anywhere from 1 below the pK to 1 above the pK. So the buffer region, we're going to get into this when we do titration curves, and that is when I have a buffer region from about here to here. This is roughly pK minus 1 to about pK plus 1, because that's what these two give me, and then pK in the middle. So how many have seen this curve when you do titrations? How many are familiar with that curve? So it starts up, it levels off to form the buffer because pH doesn't change much. It's ever so slightly increasing, goes up. But the buffer region starts around -1 up to around +1. Arbitrary amount that chemists give you. Okay. Buffer again, mixture of HA and A minus in roughly equal concentrations. Roughly equals anywhere from 1 over 10 to 10 over 1. All righty, hopefully this seems okay. So again, buffers go from about pK -1 up to pK about +1. So the range of a buffer is typically around 2 pH units. Oh, yeah. So with that in mind, what we did, we covered acids, we covered diprotic, we covered Lewis, we covered oxyacids, we covered strong. So all we can do now is say Adlos. This was an L for Lewis, but that covers everything. Again, sorry, went a little bit over time, but Adlos. So what's our official farewell from now on? Adlos. So that covers that. Hopefully it seems okay. If you need me to go back to something, please let me know. Oh, you're very welcome. But hopefully this gives you the foundation. I'd love to you too. So yeah, I'm hopeful that this covers the basics, but also makes it clear that bio, OChem, GChem, uh, they all tie together here. Physio, biochem, you have to know your acid-base chemistry. And just off the top of your head, know all the areas that can have pH impacting them. The four we mentioned, the pancreas, the small intestine, the lysosomes, the stomach, but also does it show up in the kidney? Oh, my office hours, good call. My office hours are Mondays, 4 to 6. Well, actually, I'm going to keep writing it as this 4 to 5 plus. We go 2 hours every time, but this encourages hopefully people to show up early. Sorry, Sunday, 5 to 6 plus. And the same link you did today. And would it be worth me sending out an email again with the link and everything? Even though all of you made it here, but in general, how many just gotten so many emails they're sort of lost? Perfect. Okay. And yet, and just quick question, how many find that the Discord page is working way better than the portal? It is so better. Yeah. And thank you so much, Jonathan. Seriously, thank you so much for keeping that thing alive, because yeah, everything you need. Now you're gonna have to go to the portal to get access to the exams when that finally happens. But it just seems like the Discord is a little bit better. It is much more centralized. And also, how many are getting some benefit out of, at least early on, being able to vent? And you're going to see the culture of the Discord page is going to totally change from venting at first to like support and helping each other and study buddies. And you can already start feeling it starting to change the culture. Yeah. And it's just because, again, you guys are really, really good people. And now you have a way to communicate and coordinate with each other. And so, two of the best things that happened online, the private chat and Discord, those are two things that seriously make, and it's not our class better, they make all student interactions better. Yep. You're starting to get it. In the first few weeks, how many are just tired of being stressed? It's like, I'm never going to finish it all. It's like, yeah, you're right. You're not going to finish it all. So what? Finish everything you can, be as prepared as you can, keep plowing away. But how many have discovered the art of saying, so what? And it feels kind of good. Yeah. And you get tired of being tired. I know it sounds like such a weird sentence, but yep. Yeah. And once you admit it and succumb that I'm not going to finish everything, but you don't need to finish everything, then you start going to the next phase of the preparation. What is the best thing for me? And once you make that question, that's where you're there. And phase one, and it's going to fluctuate. By the time you get to later chapters, you're going to find your phase one scores are going to go up. Early on, it's learning the game and learning how to do it. But just if you can be around here, 56% on phase one, 14 out of 25, around 62% on phase two, and 67% on phase three. If you can be around there, now occasionally you're going to have a sub 50, and occasionally you're going to have a 70 or something. It's going to fluctuate. So don't take local, take the big picture. But if you're doing that, you should have every reason in the world to expect a 127 to 128, probably closer to the 128. Yeah, I'm trying best to avoid that mentality. But yeah, and yeah, okay. Deep breath, but this is the actual numbers of data collected for the GChem, OChem, and physics. he might be talking about bio. So I think, oh, on the MCAT. So on the chem physics section. And again, I so apologize. I am being so chem physics centric because that's what I write and that's what I've kept track of. But yeah, if you end up, you should see this progression, about 14 out of 25, about 15 and a half out of 25, and about 2 out of every 3. And those people go on to get about, on the old test, like high 10s, low 11s. On this test, high 127, low 128 for the MCAT score. And it's, yeah, it's probably 85th to about 91st percentile, somewhere in that range. But don't focus on the numbers. If you have to have them, they're there. But are you worried about what you get now or what you get in January? And that's, it's just, you got to keep telling yourself that. I don't care if I keep tripping right now, I will be fine later on. Yeah, it's definitely not worth it. And you're also trusting that your path is the same as everybody else that I've averaged in over the years, and it's just not. And it's just, yeah. And doing well in these is no guarantee you'll do well here. Doing poorly is no guarantee you'll do poorly. It's a message that you got to, I don't know, just adapt and adjust. The biggest thing is not what you get, but what could you get if you saw these questions again? Not what you get, but what could you do if you saw these questions again? Getting better is key. And even then, that's no guarantee because it's all over the map. There might be one passage just totally weird. It's going to screw up one of your scores. You're so welcome. Thank you guys. I mean, it's going to be hard to finally let go, which I'm probably going to let go in January for good. It's going to be so hard because honestly, it's fuel. You guys don't, I mean, you see how much you motivate each other? It's so awesome. The way you guys motivate each other is also motivating from my end, and I'm liking it. And so at some point, I know I'm going to have to keep doing this. Nah, I will not be making my own. I might do tutoring. I'll probably end up doing tutoring because I think I'm going to miss it too much. But yeah, the whole course concept, I'm just done with the course concept. I think, especially what you set up in Discord, is that the best part of the course? Being totally honest, is your hard work in Discord to set the thing up in the group. How many would agree? That's probably the best part of the course. And all you need is a bunch of strangers with good common perspectives come together. Yeah, exactly. Just toss those in there. Yeah, and that's what I want to try to toss in there. And eventually I'll end up doing that, coming up with some sort of YouTube page, or I might just, if I can find somebody who can host. I mean, I don't know what it costs, maybe 10, 20 bucks to subscribe to a channel like that. But I don't want to make any money off it anymore. I'm done with that aspect. I seriously just want to detach. But if I can find somebody who has a good website, if they get 20 bucks a head for people to come in and be able to watch any and all the videos, that hopefully will pay for their light bulbs and whatever they need to do to keep it going, and I can just be like removed. That would be perfect. I'm trying to catch up. And thank you guys. I mean, actually, it isn't the best. I mean, you guys are just so amazing. And again, everybody who wants to go into this field right now, you're just amazing. Yeah, I don't think it's all that expensive to run a website. I'm assuming if you had 100 people paying 20 bucks each, that would pay for everything. I mean, that would even like pay for, on top of the hosting, just the person who wants to set everything up. Yeah, these are things I don't know about. But yeah, there's enough free things out there. We still have to, I mean, somebody has to manage it. So just enough money for somebody to do it. Okay, I might tap into that. I would have to understand what Twitch is. Isn't Twitch gaming? By the way, is this all being recorded still? Not that anybody records everything. Yeah. Yeah. You wouldn't mind, so that